So we have to talk a little bit about what energy is. Chemists mostly study matter, but energy affects matter, and so we have to deal with it. So energy, that word in science, is defined a little differently than how we use it in everyday life, right? I just finished an energy drink, right? Sugar-free Rockstar Punched. Makes me feel better. Gives me energy, right? Scientists define energy as the capacity to do work. Now that's not completely at odds with our definition of how we use energy in everyday life, but it's more specific. It's the capacity to do work. Well, what's work? We have to define that then. We end up defining all kinds of things. In science, work is a force acting over a distance. So energy equals work, the capacity to do work, and that equals force times the distance. So if I take this wash bottle of soap and I push it across the bench, that's work. I applied a force over a distance. Now, did anybody give me money for doing just that right now? Not directly, no. So, we talk about work as something we do that we get paid for. But that's work in the scientific context. So, energy, capacity to do work. Heat is related to energy. Heat is a flow of energy. So heat is energy moving from one thing to another. It's a flow of energy based on temperature difference. So you've got a cup of soda and it's warm. Why do we put ice cubes in it? To make it cold. Well, how does that work? Well, the soda was warm because it has a higher average kinetic energy. The ice cubes are cold because they have lower kinetic energy. There is a transfer of energy from the warm soda to the cold ice cubes, resulting in the soda getting cold. That's what heat is. It's a transfer of energy based on temperature difference. We've got the Fisher burners going here because the classroom's cold. We had a chemical reaction there generating energy, and it's going from the hot flame into the cold air. That's heat. Energy can be exchanged between objects through contact. Like you've got that chemical hand warmer. It's transferring energy to your hand. It's warming your hand. We can also have energy being exchanged through collisions. So things bumping into each other. Energy and heat can be hard to get straight in your head. So energy is a quantity that something can have. Heat and work are two different ways that an object can exchange energy with other objects. So you can exchange energy through doing work. You can exchange energy through heat. But energy is the thing that stuff has. Okay? Energy can move out of an object or into it. That transfer is heat or work. There are different kinds of energy. So we've talked about kinetic energy. Kinetic energy is the energy of motion. Objects that are in motion have kinetic energy. Thermal energy is a form of kinetic energy. Thermal energy is associated with temperature. It's a form of kinetic energy because all particles are moving. The particles in the bench, the particles in the floor. They're not moving relative to each other. They don't have kinetic energy in the sense that they're traveling through space, but they're moving back and forth within a small region. And so they have kinetic energy. You heat them up, they wiggle and vibrate more. That's how their kinetic energy increases. So here we have the pool table, cue ball coming over here. It has kinetic energy. It hits this purple ball. There is an energy transfer. Work is done on the purple ball by the white ball, and the purple ball goes shooting off. And so now the kinetic energy that the white ball has been transferred through work to the purple ball. It's kind of getting into physics too, isn't it? So kinetic energy. Potential energy is energy stored in an object or energy that's associated with the composition or position of the object. So potential energy can be stored in the composition or it can be stored in the position. So positional potential energy is a little easier to understand. Here you hold this ball above the pool table. It has gravitational potential energy. It is raised above a surface and gravity is pulling on it. You let go of it and it falls. I learned not to do this with chalk. So I carry this dry erase marker around. So I've got this Expo marker, right? And I hold it out at shoulder level and I let go of it. It falls. It does that every single time. It had potential energy when I was holding it. When I let go, what happened to that potential energy? It's got much less potential energy now because it's on the floor. It's really hard to fall off the floor, right? We can also have chemical energy. Chemical energy is a form of potential energy. This is associated with the relative positions of particles in the matter. So the positions of the charged particles like the electrons and the protons, how they are arranged can cause chemical energy. That is a form of potential energy. It's stored. It's not related to motion. So energy is the capacity to do work. We've got kinetic energy, potential energy, and then subcategories here, thermal energy and chemical energy. And there are other distinctions, but these are the ones we're going to need the most in this chapter, thermal energy and chemical energy. Any questions? So some other forms of energy, electrical energy. That's kinetic energy. It's associated with the flow of electrical charge. Electric current is movement of electrons, and so that's a form of kinetic energy. We've got heat, also referred to as thermal energy. That's the kinetic energy associated with molecular motion, so particles moving. Yeah. That's a good question. We're supposed to memorize all of these. No. You need to know potential, kinetic, chemical, and thermal. Those four. You need to know what those are. Light is energy. It's also called radiant energy. And this has to do with energy transitions within an atom. We've got nuclear energy. That's potential energy that's stored in the nucleus of atoms. And then we've got chemical energy. This has to do with how atoms are relating to each other and the charged particles within them. So energy is conserved. I think we've talked about that. Conservation of energy. So the law of conservation of energy says energy cannot be neither created nor destroyed. That's that's a double negative. Well, let's just do this. Energy cannot be created nor destroyed. I don't know where that came from. So when energy is transferred from one object to another, the total amount of energy remains the same. You can't have something that's generating energy. It can only take an existing form of energy and transfer it into something else. So, I picked up the marker. So when I drop the marker, so it has potential energy up here. When I let go of it, now the potential energy is less. Did I just destroy energy? No. As the marker fell, it moved faster and faster. Its kinetic energy increased. So the potential energy was converted into kinetic energy. Then what happened to that kinetic energy when it hits the floor? It's released as heat. When two things collide with each other and it's inelastic, that energy goes into heat or thermal energy. Now, with something that small, just with your hand, you wouldn't be able to measure any change in temperature. But if you have, the right instrumentation, you could measure the change in energy there. Here's another example in this picture. You put a ball on a spring. This has mechanical potential energy. So you push down on the spring, and there's potential energy in the spring. You release that, the spring expands and takes that potential energy, converting it into kinetic energy of the ball, and the ball goes up in the air. So this idea, conservation of energy, is really, really important. Now, sometimes it seems that energy is being created or destroyed or lost, and it is not. We just are not aware of either where it's coming from or where it's going to. So when we talk about transfer of energy, we have to define what we're looking at and what it's transferring stuff to. And so we talk about a system and a surrounding, the surroundings. And so how you define system and surroundings can change. It could be different in different problems. You can look at the same situation and define things in different ways, but we just have to figure out what is the system, what's the surroundings. So the system refers to what we're interested in, the material or the process in which we're studying energy changes. The surroundings are everything else, technically the rest of the universe, okay? Normally, we don't have to consider the whole universe, usually just the space around what we're interested in. But we look at the exchange of energy between the system and the surroundings. I think of energy as being a lot like money. Money is something that you can have, right? Energy is something that an object can possess. Heat or work is the transfer of energy. So when I pay someone money in exchange for an object, then that's more like heat. I'm transferring the money. So we have to define who is paying the money and who is receiving the money. And that's sort of what we're talking about with system and surroundings, okay? Defining the two parties. So conservation of energy. The energy that's gained or lost by the system, the part of the universe that we're interested in, has to be equal to the amount of energy gained or lost by the surroundings. So here our system is half full with energy, and then after we transfer some energy to the surroundings, then it has less energy. Here, the surrounding energy gauge is a quarter full, and after this transfer from the system to the surroundings, its energy gauge goes up. So the energy lost by the system equals the energy gained by the surroundings. The form of the energy can change, but there's no net gain or loss of energy. Well, energy is a quantity and it can be measured, and so of course we have to have units. The amount of kinetic energy is directly proportional to mass and velocity. We've talked about this a little bit. Kinetic energy is 1/2 mass times the velocity squared. The unit in the SI system for energy is the joule, and the abbreviation is a capital J. This is a relatively small unit, and so we oftentimes are talking about kilojoules when we're dealing with reasonably sized chemical reactions. So it's a unit, and you can apply all of the metric prefixes to it. A kilojoule is 1 × 10⁻³ joules, or 1,000 joules. Okay. Just for reference, if you think about a typical light bulb, 0.10 kilowatt hours of energy used in an hour. That would be the equivalent of 3.6 × 10⁵ joules. So compared to kilowatt hours, joule is a really, really small unit. The joule is defined as the energy needed to move a 1 kilogram mass a distance of 1 meter. So energy is the capacity to do work, which is force times a distance, right? So force is the Newton. Newton is a unit of force. It's a kilogram meter per second squared. And then times a distance, 1 meter. And so that's where we get the kilograms meter squared per second squared. And I gave you a sneak peek at that when we were talking about root mean square velocity. When you have the molar mass in kilograms per mole, then the units work out and you get meters per second. So that's what a joule is. A calorie is another unit that we use frequently in chemistry, and this is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So if you take 1 gram of water and say it's at 25 degrees Celsius, and you increase the temperature to 26 degrees Celsius, the amount of energy you put in there is 1 calorie. So, of course, there's a relationship between calories and joules. 1 calorie is 4.184 joules, and that's an exact conversion. Of course, we're familiar with calories. People talk about calories in relation to food, right? Dieting, trying to lose weight, cut calories, etc. The calorie that we're talking about there is the nutritional calorie. This isn't confusing at all. That's a calorie with a capital C. And that's actually a kilocalorie, 1,000 regular calories. So calorie has the abbreviation CAL. Nutritional calorie, when we're talking about food, is a capital C. I'm not doing this to you. Don't blame me. Don't blame the messenger. So this is a relationship that you should know. 1 calorie is 4.184 joules. A nutritional calorie is 1 kilocalorie, which is 1,000 calories. You should know those. Here's a table that's, maybe interesting. No, this is the one that might be interesting. These are conversion factors. So calorie to joules, nutritional calorie or a kilocalorie is 1,000 calories, which would be 4,184 joules. Kilowatt hours, that's what the power company uses, PG&E. If that was needed on a test, I'd give you the conversion factor. I don't remember that one myself. And then this just kind of gives us different quantities of energy. So like the amount of energy used by the human body in running 1 mile. Okay, so you run a mile, you burn 100 calories, nutritional calories. Well, that would correspond to this many joules. That would be 1 times 10 to the 5th regular calories, or 0.12 kilowatt hours